At this point, we're making really excellent progress through this course. We've seen quite a lot of things, and I'll scroll down to look at this picture here. We've seen in Chapter 1 how to do the kind of voltage measurements and current and temperature measurements that are needed as inputs to the other battery algorithms that we've talked about. In Chapter 3, we talked about estimating the state of charge and, in fact, the entire battery state for a battery cell model. We talked about estimating what is the present state of health and the parameter set of the model equations. And we just completed a unit that talked about how do we balance battery cells and why is it necessary and how quickly do we need to do it and so forth. We now turn our focus to this final topic of computing power limits. And we're going to study this in two chapters from two slightly different perspectives, actually quite significantly different perspectives. And it all depends on what you're trying to optimize. A power limit is going to tell us how quickly we can add or remove energy from the battery pack without violating some set of design constraints. And these design constraints may be a number of things. And that's why we have two different chapters, because we have two fundamentally different ideas for what design constraints might be. In this chapter, our assumption is that the primary design constraints are on cell terminal voltage. As long as we keep terminal voltage within some limits, then we have not delivered too much power or received too much power. That is the assumption, and that is the common practice today. And this is an indirect way of trying to minimize cell degradation, because we know that if the cell voltage is too high, the cell will degrade quickly. If the cell voltage is too low, the cell will degrade quickly. And if we keep the voltage in a certain range, then the cell will tend to last longer. So voltage is an indirect way of ensuring if I control voltage, I can indirectly control life. But it's indirect. If we could have some way of calculating more directly what the damage would be if we had certain power demand at a certain point in time, we could more directly control life, and we could perhaps even allow more power in some instances than using a voltage limit, or sometimes we would in fact say that less power is available. But we would more directly extend life by computing power limits that way. So in this chapter, chapter 6, we will focus on voltage limits. In chapter 7, there will be an introduction to some physics-based power limits, but an in-depth discussion of that is beyond the scope of this course. It's more an introduction into where I think the field is moving in the future, and I've seen ample evidence in recent publications and research projects that people have been funded to work on. In this, that's what you say here in Chapter 7. We're going to look at some ideas, some advanced ways, some thoughts for how we might compute power limits based on incremental damage so that we minimize that rather than using simply terminal voltage. In this section in this chapter is very short, and it's an introduction to some of the ideas that we will be implementing in the remainder of this chapter. And in fact, the overall chapter is pretty short. It's not a very complicated idea to compute power this way, so we'll go through it fairly quickly. The traditional voltage-based power limits say that the terminal voltage of this cell is not allowed to exceed some maximum voltage or to be lower than some minimum voltage. And the nature of the calculation of power is not instantaneous, although we recognize that power is itself an instantaneous quantity. But the calculation that we give for power limits are delivered to the primary load controller, whether it's a vehicle controller or whatever, to say this is the maximum power that is permitted to be drawn from the battery pack or to be sunk by the battery pack over the next delta t seconds. It's a predictive quantity. This picture attempts to show that. So right now I'm right here in time, and the horizontal axis is a time axis. So right now my job is to compute a number, a power limit number valid for the next delta t seconds in the future, such that if I say 10 kilowatts, the load is permitted to draw 10 kilowatts continuously for that delta t seconds, and I am guaranteeing that no damage will be done if that happens. If the load draws 10.001 kilowatts, then I say, oh, no, all bets are off. I said 10, you did more than 10, and so I could write that down in my logbook that the load exceeded the prediction. But as long as the load stays within the limits that I tell it, that it is not violating any kind of warranty things. So if I'm computing the power limits wrong, that's my fault, and if in fact I damage the battery cells by doing it, that's my fault. So this power limit thing is pretty important, just in terms of who pays for warranty claims if the battery pack dies prematurely. Is it the people who make the battery management system because they did bad power limits, or is it the people who designed the load because they exceeded the power limits? In any case, the number I provide says you may have this amount of power constantly or less over the next delta t seconds. However, I then refine that value much, much, much sooner than delta t seconds, so that I make another estimate at this point in time, and another one at that point, another one at that point in time, so that over the course of that original delta t seconds, there's tens or hundreds of updates to what that power is. And of course, we're predicting farther into the future. We're moving a little bit into the future every time we do it. However, it does allow us to compensate for, at least a little bit, for an overly optimistic power estimate at the beginning. So if here I said 10 kilowatts, and I changed my mind and said, oops, it's really 9 kilowatts, well, the load is going to have to ramp down to 9 kilowatts for the next delta t seconds starting here. So as long as no damage happened in this short time interval, I am actually safe. However, we don't want the power limits prediction to change too much, too rapidly. We want them to be as accurate as possible, in which case they would change fairly slowly over time and smoothly, because if I have an abrupt change in the power limits, the load is going to have to obey those, and maybe it's going to cause very non-uniform performance and a perception of bad drivability if it's a vehicle or something like that. So it's predictive over delta t seconds, but I get to update my prediction much more quickly than that. Usually the delta t seconds is on the order of about 10 seconds, although I've seen it as high as 30 and as low as 2 seconds. And the update rate I've seen as fast as about 40 times a second, although if you have a really good estimator, there's no real reason to think you would have to update it more quickly than once a second maybe, or twice a second at most, because the battery cells really don't change their internal state that rapidly, as we know. The problem that we're addressing in this chapter can be described in a somewhat formal way as the first objective being based on present battery pack conditions, which means the temperature, the state of the cells, the age of the cells, all of this. We want to estimate the maximum discharge power that may be maintained constant over delta t seconds, as we've described, that will not violate preset design limits on cell terminal voltage, on cell SOC, on a maximum design power, or a maximum design current. Voltage is the primary limiter on this, and the hardest one to compute the power to meet cell voltage, but we do also put limits on state of charge sometimes so that we don't go outside of certain bounds. On some maximum power that maybe the load is rated for a certain maximum power, so we don't ever give a number bigger than that. Or current, possibly the electronics are also limited, or the wiring is limited to a maximum current, and we would then make sure that the power that we predict does not exceed that design current. That's on discharge. We do the same thing on charge. So again, based on the present battery pack conditions, the temperature, the states of all the cells, the ages of all the cells, whatever, estimate the maximum battery charge power. So here it was discharge, here it's charge, that may be maintained constant for delta t seconds without violating preset design limits on cell voltage, SOC, maximum design power, or current. And we would generally provide both of these limits simultaneously, so it's a limit of positive and negative power, if you will, that's permitted over the delta t seconds. And most cases we do both. We provide both discharge and charge power limits to the load. The notation we will use in this chapter, we say the number of cells in the battery pack is n. Cell voltage, this is terminal voltage, for cell number little n in the pack is V sub little n of t. And we are assuming there are design limits, Vmin and Vmax, between which the cell voltage, the terminal voltage, must always exist. The state of charge is Z sub n for cell n, and there's again limits on that. The power is P sub n with limits on that. Current is I sub n, and there are limits on that. Any particular limit might be removed from consideration by replacing its value by plus or minus infinity, as long as our computer arithmetic system is able to handle that as a valid value. That way, so if Pmax is less than infinity and greater than minus infinity, that really removes any limits on power specifically. So we can do that. And any of the limits may also be a function of temperature and whatever other factors there might be pertaining to the present battery pack operating condition. So perhaps it's in some kind of a limp home mode if there was a failure of the battery system, and so we put smaller power limits on it so that we can still move the vehicle but with less capability, so that we try not to cause damage, but we try not to strand the driver on the side of the road either. Temperature is a big one, because at very cold temperatures there can be problems with lithium plating if we overcharge, and at very warm temperatures we're generating heat as we operate the battery, kind of an I squared R kind of heat, and so we might want to limit the current going through the battery so that we limit the extra generation of heat, because we don't want to overheat the cells. So these limits may be dynamic limits, but at any point in time, I know what the temperature is, I know what the present operating dynamic mode of the battery pack is, so that these will be constant values right now, although over time they change slowly. Different cells might have different limits if that's desirable. I'm not sure why it would be, but it could happen. There's nothing that says that in this math that we'll introduce that that's impossible. And here we're going to assume that discharge current and power have a positive sign, and that is consistent with our cell model, and charge current and power have a negative sign, and that's also consistent with our model up to this point. Other conventions are, of course, accommodated by just math changes to change the sign of different quantities. In particular, it's quite common when reporting power limits to report a positive number for both discharge and charge power. So you're really returning the absolute value of power when you do that, which is a little bit easier to understand, rather than for charge power having -5 actually be more power than -1. That seems weird. So sometimes the designers choose to use positive values for both. So the battery pack has NS for number of series cell modules connected in series, and each cell module is NP individual cells connected in parallel. And NS is bigger than 1, and NP is bigger than or equal to 1, and N is the product of those two. Those are the preliminary definitions required for this chapter. It's the basic idea. And now we proceed to look at a couple of different ways of computing power to meet these needs.